Okay. Okay, ladies and gentlemen, I hope you can hear me all right. What I see at this point is a bunch of black rectangles, but all of you should have a nice little reactions button at the bottom of your screen. And who was the first? I think Rifat was the first. Anna Paris did that. Daniel Borisov, Maxim Cronin, RD. Yes, thank you so much. You're doing so great. Yes, yes, yes. Please, please, please keep on doing that. Thank you so much. You haven't even heard me yet. Okay, and then somebody named Kozia has sent me a red heart. I'll take care of that. Okay, thank you so much for having me here today in Perspectives of Computer Science. My name is Andreas Zeller, and it is my job to entertain you, to teach you stuff for the next, let's make this 45 minutes or so, maybe a bit longer, maybe a bit shorter, depends on you. Okay, what are we talking about today? Yes, today's topic is called illustrated code. What does that mean? And I am happy to introduce the concept to you right away with my slides. So let's see. You already heard me. Now the next question is very interesting. Do you folks at this point see my slide? I hope so. The problem is as soon as I share my slide, I no longer see things. Okay, but I see a chat window, so that's already a good thing. And let me see whether I can also get a participants window. Oh yes, thank you so much. Wonderful. I get to see some of your thumbs up. Yes, you see pixels. Thank you so much. And you see me too on my slide. Yeah, sure. These are the great slides I'm doing. I'll always put a picture of myself. No, you're not going to see this anymore from now on. Okay, good. So today's topic is all about coding and writing code in a way that it actually can be read and understood by others. I assume that most of you are first semester students, so sort of just started programming. So you should all be busy with ML and programming 1 at this point. Is that true? Let me see. Again, yes, wonderful, wonderful. You're doing great. Okay, yes. And I also see the camera has a bit of a delay, so we'll simply get out of that. You can always see me in the other Zoom, in the Zoom presenter view. So if you just look at me in Zoom, then I'll be gone. Okay, let me get out of this slide and let me point out where I come from. So, so right now I'm sitting in the CISPA building, which is a couple of 100 meters down the road from here. Of course, you know CISPA, it's a great part of, it's the latest addition, so to say, to the institutes at Saarbrücken Computer Science. And it's the former Helmholtz Center for Information Security. And I am working within CISPA, also on topics of information security, but mostly I'm working on two techniques. One is fuzzing and the other one is debugging. What do these techniques mean? Fuzzing means to throw random bytes at your program, random inputs at your program, in the hope that it actually fails. So you put in some random characters in a Word file, totally random characters, and then send this off to Word in the hope that this will actually fail, or you take a couple of random characters and send them to your favorite web service, or zoo for that matter, whatsoever, and hope to find flaws with that. This is what I'm doing here in fuzzing, and I currently have a course named Security Testing, where this fuzzing book is actually at the center of things. So this is the fuzzing book. You can actually look this up. It's in particular the first 2-3 chapters can actually also be read by people who just started programming. The other book I have been writing and for which I'm also giving courses is Automated Debugging, the idea of automatically debugging programs, finding out when and why your program fails with the help of fully automatic algorithms. Both of these are advanced courses, and if you happen to stumble across one of these in your near future, I'll be happy to welcome you in there. So normally I would have some fun today talking a bit about talking about fuzzing and debugging and everything that comes with it. And sure, do some advertising for later courses, but anyway, you will end up in my courses anyway, I guess so at least. No, today I'll be talking about something that is a bit different. Today, I'm going to talk about the techniques that I'm actually using to build these books and the techniques which I am using to build software in a way that it can actually be read and understood and reused, not least by other students. The technique I'm using here is called Jupyter Notebooks. And if you haven't heard of Jupyter Notebooks yet, maybe now is the good time to start studying them. Jupyter Notebooks are documents which put together three things, namely program code, you know program code. They put together text that actually documents, interacts with the code, and they put together diagrams that can be produced from the code. And the fun thing about Jupyter Notebook is that all of these elements actually remain part of a single document. So instead of having separate documents for code, for the documentation, for any plots or books or whatever that come with it, everything is within a single thing. And writing books or writing long documents with notebooks is lots of fun because it supports quite a number of things. It supports the concept of so-called literate programming, which means that you write about some code and you put together some text that actually illustrates it. It also supports all sorts of markup in your language. So in your text, you can make use of Markdown, of LaTeX. You can put in HTML. You can even put in JavaScript, and all this material helps in producing books that can be printed, that can be viewed on the screen, and that can also be interacted with, because you can also come up with interactive JavaScript on that. Here we have an example of me putting up a LaTeX formula in here. So this starts with $2 signs in here. And you see the typical, if you ever used LaTeX, you will recognize this instantly. Plenty of backslashes with lots and lots of extra commands. And all of this then renders as a nice mathematical formula. But you can also put in lighter updates in here. That is, for instance, to highlight things as usual in Markdown. You put underscores at the beginning and at the end of a text, and this automatically gets converted into very nice, readable web text or PDFs or whatsoever. The neat thing is also that you can have outputs and examples right within your document, which allows you to illustrate things. And you can also have quizzes in there because things are interactive. You can put up quizzes right in the middle of your notebook, and this allows you to come up with all sorts of things that may be helpful for your readers. And these rich outputs can even go beyond that. So the typical usage of Jupyter Notebooks is to have charts in there. Actually, Jupyter Notebooks are the number one tool for anyone who is in machine learning and data science, because these are the tools that you use to look through large amounts of data and to visualize things and to look for trends, such as in this very neat example here. So the plotting capabilities and the data analysis capabilities of Jupyter Notebooks are just plain awesome. But you can also put in arbitrary visualizations of your own, for instance, highlighting code. This is from my book on debugging. This is an automated debugging technique which automatically colors the individual lines in your code depending on whether their execution correlates with failure. So a line that is red in here is executed only in runs that actually fail, whereas lines that are green are executed in runs that pass. And so you can tell, okay, here's a line. It always gets, whenever this line gets executed, the program fails, it's all red. Well, maybe this is the place where the bug is, and this is precisely the idea behind that. You can come up with all sorts of formula. We've seen that before. You can also come up with other visualizations, such as this nested rectangle visualization, which is used for hierarchies. You can also put up graphs and trees and all kinds of things. This is a so-called control flow graph, which tells, a data flow graph, which shows how within a program data is flowing from one part of the program to the next. And then there are also class hierarchies. If you do object-oriented programming, you can show the individual classes of your code and show how they all relate to each other. Okay, you're doing ML. You haven't seen classes yet, so I'm going to leave that out. How about I give you a short demo of how such a Jupyter notebook actually works. And I'll just switch over to a Jupyter notebook. Here we have a Jupyter notebook. This is within the Jupyter environment. And what I have here right now is a cell. So the individual elements of Jupyter notebooks are called cells. And this is where I can now put in some piece of code, which I can immediately evaluate. The default for Jupyter, the default language for Jupyter is Python. And if you haven't learned Python yet, maybe it's a good investment. People can typically start with Python in one afternoon. But there's also environments that integrate other languages, say Java, Scala, C, and I'm pretty sure there's also ML in there somewhere. So let me start with something very simple. I'm simply going to put in an arithmetic expression in here and have it evaluated. So if I put in 2 + 2, if I press Shift Return, this automatically gets evaluated. And you see a little number on the left. This is the cell evaluation counter that you see over here. And every time I enter an expression, it's immediately evaluated. The neat thing is that the output or the result of the cell also immediately becomes part of my document. So if I save this whole thing, and if I later reload it, I'm going to see the exact results in here. And besides 2 + 2, well, you can call in arbitrary stuff. You can also say, I want, well, let me put up a hello world here. Here's hello world, and this then becomes a string named hello world. But you can also invoke functions. For instance, you can say print hello world, and then the output of print hello world will automatically come out. Now, with this, you can do all sorts of evaluations right away. So if you always wanted to know what 1 + 2, or say 1 × 2 × 3 is, there you can go. That's very easy. But you can also, of course, define functions right away within your code. So let's do something rather straightforward. Let us build a function that produces a factorial. A factorial, how do we do a factorial? Well, there's many styles for doing a factorial. I'm going to do something that is rather simple. I'm simply going to use a loop that loops over the range of 2 and from 2 until n. And every time we have that, we do fact is fact multiplied by I, and then I return the facts. So here we go. Now I have defined this whole thing. Again, I press Shift Return, and it's defined. And now I can actually use this for arbitrary purposes, in particular for computing factorials. Factorials of 3. This is 1 × 2 × 3, which is 6. Okay, I can also go and actually document this, because I can now say factorial of n computes n factorial, right? So n factorial, here we go, computes n. So this is the mathematical notation. And oops, oh, sorry. This was just interpreted as a Python cell, and this is not very good Python. Need to switch over and make this a markdown cell. And then this automatically gets evaluated as a markdown thingy. And you can see that this is now rendered as a mathematical expression. This doesn't really look like a mathematical expression. Okay, so let's do some LaTeX here. Or let's make that n is 1 times dots times n. Ah, I have it. Thank you so much. See, and now it's automatically rendered as a mathematical formula. Factorial of n is 1 times what? Well, 1 times 2 times and so on until we have n here. Okay, I realize that you folks are doing ML all day long, so actually this is maybe not the perfect style for doing this. Of course, if you do ML, you want to have this in a more functional style, so you can add that too. So let's do this right away. So what do we do here? If n is less or equal than 1, then factorial is 1. Otherwise, it is actually n times the factorial of n minus 1. And you can see this still works just as before. And since we're doing Python, we can actually make this even shorter than before just because we can. And we can make this a one-liner. So this is return 1 if n is less than 1, or otherwise it is n times the factorial of n minus 1. And here we go. Factorial of 3 is 6, factorial of 6 is 720, and the factorial of 10, this very quickly grows. Fun thing about Python is that it supports very high numbers. Yeah, factorial of 100, something you cannot do in C, for instance. How far can we go with that? That's an interesting question. Factorial of 200? Yeah, we can still do that. Ah, that's neat. If you ever wanted to know what the factorial of 200 is, so here we have it. Okay, let's stick with the factorial of 3. That's actually may make the life a bit simpler. So what you've seen here is we do have text cells in which you can put up text stuff, which then automatically gets rendered as text. And you can have code stuff, which automatically gets executed. And the output of these code cells also is included right within your document. Now this opens up a couple of interesting effects because see, in particular, as it comes to documentation, this is really nice because, say, the normal way of documenting things in Python would be something like, well, you take a text like this, and then, well, yeah, put it up here, computes the factorial of n, so you put a comment into the code. So that would be one way to do things, but you already see that this is not nearly as readable as the rendered stuff up here, because there's no way for you to integrate such a nice mathematical formula in your comment. And so, well, how do you do that? Well, maybe like this. Well, yeah, you can do that in times, So now we have to go and actually get rid of all this nice mathematical stuff in here. Also get rid of the $sign such that people can actually read it. Okay, so that would be a way to do it. Actually, if you do this in Python, then you actually make this a string. For those of you who know Python and who know the proper ways of doing things. So here we go. So this is the proper way to do things, but still, you see, you can make this so much nicer here because you have the documentation up here and you can use all the markup diagrams, colors, anything that is needed, stuff that would not be available in your code. Plus you can even come up with examples in your code. Let us give you, I'm not going to say, here's an example of how to use it. Boom, there you go. So you can actually combine documentation and examples and output all in one single document, which is, again, something that you cannot do with ordinary coding. And this, of course, features like these, of course, are all great for writing a textbook because, see, when you're normally writing a textbook, say in Word, for instance, okay, and then you copy over, so then you have to code this first, and then you copy it over into your Word file, but as soon as it's in your Word file, it's no longer executable, so you can no longer run it at your will. Whereas as long as it's in a Jupyter notebook, well, you can always execute it and always make sure that it still works as expected. Hey, you can even put in tests in here. For instance, you can write assert factorial of 3 equals 6. An assert statement in Python and other languages checks whether this condition that you have in here is actually holds. And now, if but just by chance I make any I make any change to my notebook, well, let's say I replace this 1 by 2 here. Oh, I just made a mistake. Good. So far, so good. Oh, I have a new result. Oh, good. But this assertion is now going to catch that I just made a mistake, because the factorial of 3 has to be 6 and is not supposed to be 12. So even if I make any changes to the code later on, I will automatically catch them, which is also great if you're writing, which is also great if you're writing a book. Oh, what happened to my beautiful Jupyter environment? Oh no, it's all gone. Well, that was a mistake. Okay, let me just fire this up again. And I think I pressed Command Q instead or something. Okay. Let me just fire this up again, and I will be with you in no time. Here we go. I do get a window. Do I get a window? Please get me a window. Oh, thank you so much. Voice control is so great. If I say please, things actually work. Okay, so here we go again. And I am back in the earlier state. And everything I did before actually now should be saved. So let me just see. Yes, we are still in here. And everything I told you before has been saved. It all has become part of the document in the first place. Poof, I am so lucky here. That's actually a big advantage also. See, when you're programming in a normal style, you are putting this code into your code part, so far so good, and then you're making some experiments with it, and then maybe you find out it works. But the thing is that these experiments that you do with your code typically get lost, whereas in a Jupyter notebook, they all stay in place, and you can always look up later, hey, this is what happens over here, or you can come up with an alternate. You can also go and test your code. For instance, you can go and say, okay, this is one definition here, and this is the functional definition. Here is the, oops, sorry. Here comes the imperative definition. Let's make this factorial imperative, and the other one factorial functional. Okay, factorial 3. Oh, this number no longer works. Why am I not surprised? And we can make factorial of the, oops, what did I do wrong here? Factorial fun. Factorial fun. Factorial fun. Ah, yeah, of course. Also needs to be factorial fun over here. Okay, good. So even when you're debugging, you see that you immediately see that the outputs are all preserved. So here we have a functional definition, and now I may want to make sure, okay, I want to be a good programmer here, and I want to make sure that that both of these definitions actually are equivalent. So I'm simply going to test this for the first 100 values, and I say that, and I want to make sure that both of these implementations actually return the same code, the same value. So factorial functional, factorial imperative. Woohoo! Oh yeah! Wow! Yeah, I love it. See, you might be thinking, hey, I am coding something and it never works the first time I'm entering this. Yeah, same happens with me. If I do things for the first time, if I'm doing something for the first time and it works, I am super happy. Yes, we have just proven that both of these, we have just proven that both of these implementations actually produce the same result. So if this one is correct and the other one is correct just as well, I hope I didn't make the same mistake in both of them. Or at least, well, we haven't formally proven this. We have shown this for the first 1,000 numbers. Oh, well, for the first 10,000 maybe. Let's just compute things here. This may take a while. And while it's computing, we can go back to our actual coding here. Okay. Oh, did I really? Oh, it's recursion error. Oh no, our functional version gets a recursion error. Too bad. Well, I guess we have to stick with the imperative one. Ah, too bad. Recursion error. Huh? Maximum recursion depth exceeded. Okay, good. Let's go. This was a brief demo about Jupyter Notebooks, and I encourage you to try them out for yourself. In particular, as I said, when you want to dig deep into data. But the interesting question is, and this is a new question, whether this style of writing code right within your notebook is also a general model for coding regular code that will be used in production. And this is the question I personally am pondering a lot these days, and we've started to do some research in that direction. And I'd like to show you some of my thoughts on that. So when we're talking about program code, you as beginners in program coding may think, well, the program is just my code and this is it. But this is actually not true. Besides the pure implementation that is your code file, we have a couple of more things. We have an interface. An interface describes how the code in question is to be used. So if you think of an API, for instance, here's a particular module. This module is to be used in a particular way. Then this describes the interface of how you're supposed to interact with a piece of code that you wrote. We also do have a specification. Well, at least in theory, we have specifications. Or let's say in theory, we do have formal, wonderful, beautiful specifications. In practice, we have quote specifications, quote, meaning that not all code is as nicely specified as you would like it to be. We do have rationals. Rationals meaning, why is this code as it is? Why is this code as it is? See, why is it written in that particular way and not in another way? Why aren't we handling this? Why aren't we doing that? Why are we doing it this way? This is typically found in comments in the code if you have a good programmer, but it can also be found in the history of a piece of code. Well, when you're developing large pieces of programs, Microsoft Word, for instance, then every change to the code is being logged in a so-called version control system, Git being a perfect example of that. And this is where you can later on find, why did people change things the way they changed it? And you can look this up and then also trace back the history of a particular piece of code and find out why it is as it is. There's actually researchers around who have traced back the 50 years of development of Unix code, Unix, which later became Linux, which later became BSD, which became macOS and iOS. All of this began with the implementation of Unix code. And it's very interesting to see how out of initially maybe 20 lines of code for a simple utility, you now have 2,000 lines of code for the same utility, which now has far more options than before. We also have tests. We just have seen a little test, but yes, if you want to create reliable code, you provide tests that actually test your code, and you also have to provide documentation again for these tests that describe them. If your program is large, then you do have architecture, that is, which describes how the entire big system is decomposed into individual modules. So, because you need to find your way in a big system, if you open the source code of, say, Microsoft Windows, and you find, wow, there's 4,000 files in there. What are these? Okay, you need to have some documentation that describes how all of these are actually organized. Then, if you want your code to be used by others, you need tutorials, you need explanations, you need, see, in order to use this API, in order to use this module as follows, you need to do this, you need to do that. Here's an example of how to use all that. And finally, in particular also for large-scale programming, people cannot imagine today programming without having sites like Stack Overflow or generally Google, that in which you can put in arbitrary questions on how to use a particular API or how to make it actually usable. So just in order to prepare this talk, I found that in my Jupyter Notebook setting, some particular module was missing. So I said, module such and such missing Jupyter notebook, and lo and behold, I found an answer on Stack Overflow how to do this. And I would not have found this in any official documentation. So, and the problem here is now, if you put all of these in separate documents, the problem is how to keep them consistent. There's even folks who say you should not write any documentation at all, because documentation invariably, in the end, does not evolve together with the code, and so the code evolves. So the code evolves, and the documentation is no longer up to date. So don't write documentation in the first place. I mean, tests and code, these need to be kept. These are consistent with each other, because if there's anything that is not consistent in there, then you're going to get a message by construction. But questions and answers, Stack Overflow, yeah, whatever. You find an answer to something, but this answer is 5 years old, and it refers to some old version of the code, which is no longer maintained. This is a total pain. Second thing is, yeah, how do you get these in the first place? Programmers are good at writing code, but programmers are not necessarily good in writing comments, let alone specifications or tutorials or Q&As or anything, because programmers are under pressure. So they just write the bare necessary, the minimum amount of code that is necessary, and then switch over to the next project. If you have some fun, go look into the actual source code of open source utilities. Say you can look up the source code of the Linux code of the Linux kernel, for instance, just to test your programmer's knowledge. If you think that you can understand the code, read the Linux code. And if you still think that you can understand it, well, write some Linux code. I don't understand this. Well, I partially understand it. I see these are all parts, but what are they all doing? This is all horrible. Yeah, that's because there is no good documentation for the Linux kernel. And so all of these things do not necessarily exist in the first place, which is a starting point. And second, they're all found in different places, which may not be consistent with each other. So the idea here is to take all these things and to put them all together in a single document. And this single document that now combines the implementation, the tests, the interface, tutorials, rationals, architecture, specification, Q&A is, well, you guessed it, for instance, something like a Jupyter notebook. Because in a Jupyter notebook, well, you see these, you have documents that are executable. It's nice. They are self-updating and they are self-checking. And I'd like to get you a couple of ideas on how this actually works. So we're going to look at a very simple example. We are going to look at a simple function called middle. Takes 3 parameters, namely x, y, and z. Here we go. This is middle with x, y, and z. And this is supposed to return the middle of 3 integers. And the middle is the one number of the 3, which is neither the maximum nor the minimum. Well, if all 3 are equal, then it is both the maximum and the minimum and the middle. But apart from that, I think you guess it. Okay, so this is what we're going to use as a simple study of how things work. We're going to look into how all of these things actually can be added into one single document to just define this. We're going to start with the interface. Interface is very simple. How do I use a piece of code? And this is not very difficult to define in a Jupyter notebook. You define the signature of the function. So I want a definition of, I want to have a function that is called middle, which has three parameters, x, y, and z, all integers. They return an integer, and it's supposed to return the middle of 3 numbers. This is the standard way of documenting things in Python and other languages. We have a comment on what the function does, which is nice. but you know, there's no formal specification. So what the middle could also be misunderstood as maybe the average of things. This can be very confusing. There is no example of how to use it, and there's also very obviously no implementation yet. Okay, let's do this a bit further. Next thing we're going to come up with is a specification. And specification describes what the code should do. And we can actually write a formal specification of what middle does using higher level programming features. For instance, in Python, we can say, okay, I'm going to make a list out of X, Y, and Z. Then I'm going to sort that list from the lowest to the largest. And then I'm going to return the second element of that list. And if I have done that, say it's 5, 4, 3, I sort this, I get 3, 4, 5. And then if I return the second element of that list, 3, 4, 5, I get 4, which happens to be the middle. Okay, that's great. Our specification actually is executable. So why bother after all? I can actually use this as I could actually go and use this as my implementation right away, but I can now also include examples of how this is supposed to work. Okay, specification is good, examples are also good, so this is enough material for me to actually implement things. And I can also put up assertions, I can use them as tests later, such that I can check whether my implementation is actually going to do the return the right result. Okay, now I have a specification. If this were ML, I would just stop here and I'll be happy with it. But let's assume I really need a separate specification in here. Note that our specification can include lots and lots of rich documents. For instance, if I wanted to implement middle as a web service, the middle web service, maybe that's a bit over the top, but I also understand that there's some JavaScript packages even for the tiniest of functions. So I can even come up with, say, okay, I want middle to be defined as a server, and the server then has a client, and the client sends a request middle of 547 over to the server. The server does a bit of work and then returns the middle function. I can also include such diagrams right within my document. So specification, because Jupyter notebooks allow all this all this kind of rich input beyond just text, all sorts of diagrams, pictures, whatsoever, interactive stuff, I can come up with very, very interesting specifications. I should point out that this diagram was created with 3 lines in Markdown using the Great Mermaid extension. So you're writing some text and you're simply adding these 3 lines. So wow, technically speaking, it's 5 lines, 3 of which are of mermaid. So I enter this line sequence diagram and I say, the client sends things to the server sends things back to the client. And this is how I can create such a diagram in pretty much no time. Compare that with LaTeX or your favorite graph diagram. It's horrible. Okay, good. Now, finally, I want to implement this whole thing. And now I'm coming up with an efficient implementation for middle, which actually now this is pretty efficient implementation, which goes and comes up with a minimum of comparisons. We can simply look at the first 2 in here. So if y is less than z, and if x is less than y, well, which one is the middle then? The middle then, in this case, is y, because y is very obviously bigger than x and smaller than z. And we can continue this for all the remaining parts of my code. So I'm either returning y or x or z, depending on the results of these comparisons. So here's an efficient implementation for middle. You also may note that it's not only a more, so it certainly is longer than my original specification thing with sorted, where we had only one line. Now we're having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 lines. But I can actually, but since my code is all executable, I can actually go and show that my new implementation is more efficient. This is executable as well. Tests and results become part of the doc. So the reason why the code is as it is, well, is simple. We're using this particular if and return, if return thingy because it is faster. And this is something I can easily measure. Also, all as part of my document. I can make experiments right in my document and document the results of it. So here's set up a small benchmark to test a function with a number of random values. And if I measure the time with my newly defined middle function, this takes 0.2 seconds. However, if I do this with the middle spec, remember, this is the function that actually creates a list, then sorts it, and then returns a second argument. Well, we'll find that this takes about twice the time. And this is the rationale for me to actually go for this more complex code, because it is faster than the original code I wrote. Well, faster is a thing. It is going to depend on the individual machines I'm using, and it's going to depend on the environment I'm in and other stuff. But at least for now, this is a reasonable assumption. And again, these can stay right within the code, right within my document. And if anyone later on reads my document and wants to find out why is the code written as it is, that's because I have an experiment right here within the code which illustrates it. And hey, I can even come up with more alternatives, say the same alternatives we've seen for factorial. Maybe I can come up with one version and another version and a third version, and then finally pick the one version that actually provides the best performance or is the most reliable, most robust, whatsoever. And all of this goes right into my document as a rationale. And I can even have the document check whether my rationale still holds. This is important because, you see, who knows whether the experimental results are still going to be the same the next time. So what I can put in here is I could put in an assertion. You see, I'm a testing person, so I like lots and lots of tests in my, lots and lots of tests in my code. I can put in here what I've written in my code, namely what I've written in my document, namely that middle is the fastest. And I also said that middle is almost twice as fast as my middle spec experiment. I can put these as assertions in my code, and should the speed of my two implementations ever change, because Guido van Rossum has released a new Python version, or we are now using Python compilers instead, or everything is multi-threaded, or everything is parallelized automatically, and therefore there's a new functional version which can do things even faster, or we're using quantum programming by default, and now great quantum computer is going to produce the results of middle even faster, whatever. Well, as soon as anything of this happens, then these assertions that we put down here are going to fail, which then means that, hey, I have to update the documentation, and I also may have to update the results of my earlier findings, because, well, all of a sudden these things are not valuable, are not valid anymore. Okay, so what we can get with this is a consistency between the documentation and the code. And I've been talking about tests a lot. We can put up lots and lots of tests into the code. I can put up lots and lots of examples on how the code should work. And from this already, you can see a couple of examples on what middle should provide. So even if you did not fully understand what this sorted list does. Well, in here you see examples of how things work. And again, if you make any change to middle that causes these tests to fail, you will be notified immediately. And you can also analyze the test performance. You can check which parts of the code actually have been covered so far. Obviously, if you want to test a piece of software real thoroughly, you want to make sure that every line in your code is executed at least once. Because if code is not executed at all during testing, then very obviously there can still be mistakes in this very code. And because if it's not executed during testing, well, then it's going to be executed first, maybe with the customer, and then the customer is going to discover the bugs that you should have found. So we can measure the coverage of tests, which parts of the code actually have been executed. And this is something we can do just as well right within our notebook. So in here, what we see is a visualization of the source code. And we get a star for every line of code that our tests so far have executed. And we see that almost everything is executed, but there is a situation, or there are two situations, namely here and down here, which do not yet have a star. So these are test cases that we still need to add, such that this extra code would be executed just as well. And these assumptions about coverage can also be put into the document. So we can also measure the coverage, and we can say, I want the coverage to be almost 100%, and I can put this into the document just as well. And I can also come up with even more tests and come up with, this is a fairly thorough test. So we're creating 100,000 random combinations of X, Y, and Z, all between 0 and 1,000. And we check whether middle is conformant against its specification. Yes, and this again is probably going to run just fine. And this is how we can then finally verify that middle exactly works as intended. That's assuming we didn't make the same systematic error in the specification as well as in the implementation. One thing. Second thing, we're only checking values between 0 and 999 here. We're not checking negative values. Maybe that should also be something to do, but you can very easily add additional tests, and these will be executed in a second. And again, if anything goes wrong, you will be notified immediately. And I don't know who your current lecturer in programming one is, whether this is Bernd Finkbeiner or Gerd Smolka. I know that both of them actually are very big proponents of Smolka, thank you so much, are big proponents of symbolic reasoning and symbolic verification. So within your document, you can even go and say, and you can even go and create a formal proof of your implementation. Because, well, so far we've only tested our middle function with 100,000 random values. Is this enough? Are we really 100% sure that it's going to work at all times? Well, we can do so by invoking what we call a so-called symbolic constraint verifier. So we create a solver that is going to find, is there any solution for a particular formula? And what we do with this is for you to try out at home if you like to. What we do with this solver is we create four symbolic variables, X, Y, Z, and middle, which all are integers. And then we say, dear solver, here's a couple of constraints. For instance, we say that if Y is less than Z and X is less than Y, then middle should be Y. This is exactly the same as the if chain that we have in our implementation. And we're encoding one constraint after the other this way. If y is less than z and x is greater or equal than y, this is the else branch, then middle should be x. Okay, so we're converting our entire program into this formula, and we're converting our entire program into this formula, and then we're telling the solver in another thing, okay, now if x is less than y and y is less than z, is it possible that middle is another value but y? Okay, obviously y is the middle value in here, and we tell the solver, please find a solution that where middle is not y. Okay, and then we have the solver check this entire set of constraints, and the solver returns unset for unsatisfiable. There is no way that middle cannot be y, which in turn proves that middle has to be y in here. So we have just automatically proven correctness of our program. Just to do some expectation management, no, you normally will not be able to encode your entire program into such constraints and have the solver prove correctness once and for all. As soon as your program has loops or recursion or array indexing, pointers or anything, you will have to put up quite some manual work in order to prove programs correct. However, if you can prove that your program is correct, then you're super lucky, because then there's no way it can fail. Wow, why you don't have to test it anymore? You're done. Everything is just going to be perfect and hopefully remain perfect. Of course, again, you can keep those constraints and those proofs right within your document. And every time you change something to your code, should somebody come along, you can still use the solver to check your program very thoroughly. You can also come up with architecture diagrams. You can have them either in the specification, but you can also extract them right away out of your code, which is neat. Visualizing what's happening in your, what's actually happening in your program. So here's a simple server. The server is our middle server, which provides a couple of services, middle, min, and max. And you can visualize this as a class diagram, very neat. And the class diagram then gives you an abstract representation of the server, its state, and the individual services it provides. And you can even extract such diagrams dynamically, which then give a visual representation of what's happening between the client and the server. So here's a simple example. I have implemented earlier a small helper function, which is called sequence diagram tracer, and everything that happens in this with block will automatically be traced. So it is going to record all interaction between individual elements, and then we can eventually show this, and this becomes another neat diagram in which we can see the interaction between the client and the server. And all of this, again, always remains a part of your document, and it automatically gets updated, and it automatically can be checked against whether it still is up to date. So finally, you can also put in instructions on how to run things with examples, and you can even execute these just as well. This makes sure that your tutorials actually are running well together with the original code, which is very helpful. And executable all the time, testing the tutorial. And you can even imagine that your document could even contain a piece of, this is not in Jupyter Notebooks right now, but you could imagine that it could contain a piece that would actually be shared among multiple people, where people can add their own questions to the document, and answers can also be provided by others. You could rank answers up and down, whatsoever. And the neat thing here again is that all of these questions would be executable, and the answers would, of course, also be executable, meaning that if any of these answers no longer work, well, you would be notified immediately because you would see an error message. And this can either be a call for coming up with a better answer, with an updated answer, whatsoever. If you're working in modern environments, I always say things change and then you have to change as well. If you're working with modern environments, it's amazing how many changes you have to cope with. So somebody updates module X, it gets published, somebody else imports this, somebody else has to adjust things. You'd think you'd program something and then it would stay there forever. No, you have to keep on updating your things and put in security updates, put in feature upgrades, whatsoever, all the time, just to stay in touch. And this is why we have all these many questions and answers that also need to be addressed. Okay, so this is what we have seen with illustrated code. Everything in one place. And this is something that you can already try out yourself. Having things in one document, having rich documentation. Everything that you do is computable, checkable, and repeatable. It's fun to read. It's definitely more fun to read than source code, because see, if you have a tutorial, you put in a tutorial, then you can explain to others how things work. This is, of course, effort upfront, but believe me, once you have, if you take a piece of code that you have written and look at it, say 6 months later, you're going to have a hard time understanding what it was about. But if you still have an example of how it works, and if you wrote yourself a couple of lines, here's how to use this whole thing. If you just wrote this to yourself, then others will be able to pick this up and possibly even extend this. So there are many ways. So this is the important thing. When you're writing code, you're not writing things for the computer. You are not writing things for yourself. You're writing things for others to read, because in professional software development, every line of code that you write will be read by 10 people, 20 people, if it's open source, several thousand people. And therefore, all the effort you put in there in making your code readable, understandable, and up to date will pay off 1,000 times. Okay, actually, all of the things that we have seen so far, I actually also have implemented them for the fun of it. So we can again have a short look at things, also to recap things. Here's my middle implementation. Interestingly enough, in Python, 3 dots are actually part of the language. This is the so-called ellipsis object. And you use this to show that there's something missing somewhere. Okay, here's an interface for middle. This is how we are supposed to implement the middle function. Well, here comes a more detailed specification. Here comes middle spec. And this, again, takes this list, sorts this, and takes the second element. And yes, we can go and execute this right away. 543, well, that's one thing. 544 is 4. 444, what's the middle of 444? Probably 4. Which 4 is it? That's not specified. All these 4s are equal. Okay, let's make this again 5, 3 for the fun of it. Here we go. And you can also have an assertion that does that. And your specification can have all sorts of diagrams in here. And just for the record, this is how you can create such diagrams. If you want to replace 547 by 534, for instance, boom, you do this and the diagram automatically gets updated. So this is really, really cute. No need to switch over to some diagram editor or whatever, because all of this becomes inconsistent after time. Okay, here's the actual implementation. We've seen this before. If y is less than z and if x is less than y, then we have to return y. Why do we have to return it? Well, by the way, elif is the same as else if. This is just a short form in Python. Return and the other stuff, you should have seen this before. Here I'm creating a benchmark that takes 3 random numbers and then uses a Python feature called the performance counter to count how much time actually evolved. This is how I get to these numbers. Oops, sorry. I guess I should execute this before I actually get to it. So what we're doing here is I'm running the first benchmark, and I am running the first benchmark, takes 0 to 47 seconds. Second benchmark takes, wonder, 0.73 seconds. Okay, that's not exactly twice as fast, but it's still, definitely middle is still faster than our original test. Then I can put up tests in here, which show how this would show the expected result for a various number of inputs. And I can even capture the coverage of my code, finding out which parts of my code have been executed so far. Let's actually just do this for the fun of it. So here comes my code, and we can see which parts have been executed already. By the way, if I just execute, say, this test here, you will see that the coverage changes. So if we only put in 1, 2, 3, then only these 3 lines will be executed. The rest has not been executed. So we definitely need more tests such that the other lines would be executed too. And here we put in the remaining, we generate inputs for the remaining lines. And now if we do this, then we find that all of the lines in the code have been executed, except for line number 2, which is a comment line, which is never executed at all. Okay, and I can also go and check things against the specification. For 100,000 values, middle is identical to its specification. We can draw neat little architecture diagrams from programs. So even if I change the name of this method to minimum, then it's automatically going to be adopted in our documentation just as well. Maximamu, did I just say maximamu? Maximum is not what I meant. Maximum, here we go. This is a dream for, I have to say this is a dream for writers of tutorials, because when things change, you always have to go through the entire Word file or LaTeX file and find out, oh yeah, now I have to update all these diagrams, all these pictures, all this code again. Here you do all of this automatically. Likewise for examples. So this again is an interaction between our client and our server. And as soon as I put in any numbers in, any numbers in here, let's make it like this, then this also automatically gets updated every time I'm doing this. So, and yeah, we also have a tutorial including instructions how to install things. This is going to be fun. I have no idea what happens if I actually do this. Oh yes, and that's because it's so quiet. I'm going to do this way, and then it's actually going to put out all the individual. So I can have command line interaction in here, and this will automatically be executed. So here we go again. We install it, and then once I have installed the package, I can actually go and execute it. And here comes the neat part for all of you who are interested in automated program proofs. You can automatically check the program for whether it is correct. And in this case, the whole thing is correct if middle actually is. Can actually turn this around. Is middle going to be equal to the thing? Not satisfiable. Why does it say so? Oh well, interesting. Why doesn't it say so? It should be actually. Okay, good. Well, seems to be unsatisfiable under all circumstances. I'm going to check this. Okay, and finally here, question and answers part, where you can put up arbitrary questions and arbitrary answers. Okay, I think I'm simply going to share this whole document with you later on, such that you can have some fun with Jupyter Notebook yourself, and also have some fun with trying out what's happening in these individual pieces of code. Okay, this was another demo where we're putting all these things together, and I think it's about time that I close things. So, what we have seen today is illustrated code that comes with illustrations of how it works, why it is as it is, how it should be. We have seen that the current status of program code is that it's distributed across lots and lots of different documents, which is a pain. I have brought up the idea of bringing all of these things together in a single document, which allows that. And so far, the best candidate for doing this is Jupyter Notebooks, which implement lots and lots of the features that would be required in here. I've shown you how to make use of the, I've shown you how to make use out of the very rich annotation and documentation features of Jupyter and its APIs, or how to write these yourself even, in order to produce documents that are very, very nicely readable, always up to date and always checked. But there's also something to be done. The thing is, Jupyter notebooks do not even come close in terms of comfort to your favorite integrated development environment. So if you're using something like IntelliJ or Eclipse or Visual Studio Code, you will find that these are way more powerful as it comes to, say, refactoring code, searching through code, and others. And the interesting question is, should we make these Jupyter notebooks more like IDEs, or should we make the IDEs more like Jupyter Notebook? There is now some very nice integration of Jupyter notebooks into Visual Studio Code, and it's getting better every week. So there's good chances of getting these things together. We also want support for other languages: C, C++, Java, Rust, Go, Scala, ML for that matter. Having notebooks is still an add-on to existing languages, which means that if you are within Python, you cannot simply go and import the code from a notebook. You have to come up with extra hacks for that, which is a bit painful. There are no good ways for collaboration within notebooks, such as multiple people working at the same time on the same notebook, or adding specific sections. These are all things that need to be done from a technical standpoint. And finally, you know, when you're coding right now, you're coding for yourself, you're writing these pieces of code, and in order to pass your exam, and then you forget about it, which is nice. But you will soon learn, when you're writing code, that this code actually lasts, and this code is meant to be read and used by others, just as you also work with code that has been written by others before. And I'm very looking forward towards a future in which tutorials, illustrations, examples all become part of standard coding. Because when we're coding, we're not coding for the computer, we're coding for all those who will read this code after on. And any minute that we spend in better documentation and better explanations is well spent in the long run. And all of this also requires more research. I do some research of that as a hobby, and I'm also following such research. And if you're interested in working with notebooks, or if you're interested in building such environments for the future, or if you're interested in automated testing and debugging, please come and see me. Oh yes, and follow me on Twitter. There I have a nice Twitter handle, Andreas Zeller, where you can find me as well. I think I have more followers than the department and CISPA combined. Yeah, you could. Well, maybe now's a good time to unfollow me. Check it out, because this is the place where I'm actually putting up on my latest and greatest results. Okay, and I think that's it, folks. So here I am. That was me, and I am happy to take questions. If we have any questions, that's a good question. I think you can, if you have questions, you can simply raise your, no, you cannot raise your hand, I'm not going to see you. If you have any questions, you can go and just type something into the chat window, or, well, maybe I can also allow you to use the microphone, whatever. And if you have no questions at all, I hope you had a good time. Thank you very much. Yeah, now's the time to use the button to leave an applause in here. That's all fine. Okay, so what do we have here? I do have a couple of questions in here. That's great. Okay, what program are you using to open the notebooks? I'm using Anaconda right now. So Anaconda is a tool to manage your Python installation. And what I'm doing here is in order to open the notebooks, it's simply invoking Jupyter notebooks. Sorry, I'm writing Jupyter Notebook. More specifically, my program is called Jupyter Lab, and what you typically need to do for that is something like conda install Jupyter, condo, yeah, autocorrect, I hate you. Conda install, no, it doesn't work. Okay, good. I'll go back to my Jupyter view here because it makes life so much easier. So what I'm doing here is I am invoking conda install Jupyter. Go. Can I actually do this? That's interesting. Okay, I don't have that right now, conda, but this is the way you work it. And once you have that, then you invoke Jupyter Notebook or Jupyter Lab, and then you immediately get access to the Jupyter environment. Conda install Jupyter Lab. See, that's the power of the crowd. Where can I find a documentation for Jupyter? Very good question. How on earth could one possibly find out what a particular program is doing? How can we find something? Oh, if only we had a magical tool that would allow us to automatically find things. Oh man, if only I had an idea of how to do that. Let me see. If I type in Jupyter, see the first link in here is Jupyter Notebook, and this actually gets, thank you so much, and this actually gets you right away into the Jupyter homepage, where you can get all the information about Jupyter, Jupyter Notebooks, how to use them, and all the stuff around. So this is all available. And the URL here is jupyter.org, of course. Okay, what else do we have? From a lawyer, is it for complex code? Okay, actually, Jupyter is also a great environment for learning how to program. And well, the question is, do data scientists need complex code? Not as complex as an operating system or as a compiler, but it can also be complex. It can also be complex code in the sense of doing some complex ML experiments or data science experiments, and likewise. You can use it at all levels, and I think that most people who use Jupyter these days are actually only casual programmers, meaning that they are using programming as a tool and not as a means in itself. And this means that there's plenty of people who use Jupyter notebooks as beginners or for light programming tasks, and maybe even for lawyers. Next question. Where do we come to? Bettina Hilkenbach. And should it maybe used for public projects like ID wallets and likewise? Sure, anything you can program in with a regular programming language, you can also program it in, you can also use Jupyter for programming with it. The page we're currently having here, as you see, we have JavaScript, PHP, C#, Lambda, OCaml maybe, I have no idea. F#, I remember that one. Another Lambda thingy. This is R, I see R in here. Yeah, I knew all the logos in here. I think this is Python up here. The JavaScript, yeah, we had that already. So you can do the same things. You can, with Jupyter Notebook, you can program the same things as in other programming languages. It's just that that your code comes with way more text and is way more readable and understandable for humans than normal program code would be. Which actually could be a great thing for lawyers too, because even if you're a lawyer these days, you have to understand how program code works and have to be able to differentiate algorithms from logarithms and other stuff. Okay, I think we are out of questions. Oh, we have another question here. Short note: there are several law students in this course who have never wrote a single line of code in their whole life. Please keep that in mind when making up the questions for the test on Thursday. Thanks. I will do so, because otherwise I will be sued. I know that, of course. So, so there will be a minimum set of questions that will actually also cater to lawyers. I can do that because incidentally, I had law as my minor when I was studying computer science. So I studied a bit of civil law and punitive law and even state law. Because when I did law as my minor, this was right in the middle of German reunification. So so actually my professors and my seminar was actually, my law seminar actually was with people who were sitting on the reunification board, and we would be discussing live the various options for reunification, which was very interesting. Okay, I see you folks. I see you folks. You see you. Let's go. Okay, good. I'll think of something that will make all of you happy. Okay. What else do we have? No more questions. Okay. If there are no more questions for you available, Python special thanks. Yes, 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 yes. Okay. No more questions. A raised hand. A raised hand from somebody. Oh, somebody raised a hand. Okay, good. I need to get out of my screen sharing thingy here. And we need to go into raised hand. We are 1 minute over time. Raised hand. Who raised a hand? Somebody raised a hand, and I cannot. Guy raised a hand. Guy, can you unmute yourself and ask your question? Is that possible? Guy or Guy? The person who raised the hand. There's one person. You need to unmute yourself, otherwise I won't be able to hear you. Guy has lowered his hand again. Okay, this was the guy. Okay, so the guy who raised his hand, or her hand, the guy, his hand, has lowered his hand again. So I think we're done. Thank you all very much for your attention. It's been a pleasure to talk to you. And I am very much looking forward to see you in person at some later stage, and hopefully to see all your coding. Okay, have a great day, everyone, and hope to see you soon. Bye-bye.